How many resonance structures are possible for phenol? The 5 resonance structures are possible for phenol. When phenol is heated with dilute nitric acid at 298 Kelvin, you will get a mixture of orthonitrophenol and paranitrophenol. Under bromination, I am going to consider 2 cases. First case, in the presence of aqueous medium, phenol undergo electrophilic substitution reaction to give a mixture of 2 products. One is ortho products, another one is para product. Hello my dear students, I am Renuka Ashok, Department of Chemistry, Vidyashram Pre-University College, the Temple of Excellence, Mysuru. Welcome to 7th session of chapter Alcohol, Phenols and Ethers. 7th session of chapter Alcohols, Phenols and Ether. In the previous session, I discussed about physical properties of phenol like boiling point as well as solubility. And some of the chemical properties also I discussed. That is, the reactions of phenols are classified into 2 categories. Reaction due to cleavage of OH bond as well as reaction due to cleavage of CO bond. So, I discussed acidity of phenol and how do you convert phenol into esters by esterification or by acylation or by acetylation. Today, in this session, that is in the 7th session of chapter Alcohol, Phenols and Ethers, I am going to discuss about electrophilic substitution reactions of phenol. Electrophilic substitution reactions of phenol. Under that, I am going to discuss about 2 electrophilic substitution reaction, nitration as well as halogenation. Nitration as well as halogenation. And the 2 important naming reactions of phenol is, one is Kolbe's reaction, other one is Reimer-Tiemann reaction. Kolbe's reaction and Reimer-Tiemann reaction. And how does phenol reacts with zinc dust and oxidation of phenol? All the concepts comes in this session, that is in the 7th session. Therefore, my dear student, in the 7th session, I am going to deal with electrophilic substitution reactions of phenol. Electrophilic substitution reactions of phenol. Under electrophilic substitution reactions of phenol, it consists of 2 reactions, nitration as well as what? Halogenation. Next, 2 important naming reaction, Kolbe's reaction as well as Reimer-Tiemann reaction. And how does phenol reacts with zinc dust as well as oxidation of what? Phenols. Oxidation of phenol. So, let us consider first one, electrophilic substitution reaction of phenol. As you know, electrophilic substitution reaction is the characteristic reaction of aromatic hydrocarbon. But electrophilic substitution reactions of phenol more pronounced in phenol than in benzene. Benzene and it is phenol. Both are aromatic compounds, but phenols readily undergo electrophilic substitution than benzene. Therefore, phenols are more reactive towards electrophilic substitution reactions than benzene. This is because of OH group, which increases the electron density in benzene ring by donating the lone pair of electrons on oxygen atom of the OH group. Moreover, phenol is stabilized by 5 resonance structures. So, what are the 5 resonance structures of phenol? When you consider this as a structure of phenol, oxygen has 2 lone pair of electron. So, already I discussed how to write a resonance structures of phenol. The lone pair of electron shifted to sigma, pi goes to carbon. Therefore, ortho got negative charge, here also para got negative charge, here ortho got negative charge. So, out of the 5 resonance structures of phenol, you observe that the negative charges are present on ortho, para as well as ortho. As a result, the electrophile attack ortho and para position to form 2 products, ortho product as well as para product. Therefore, when phenol undergo electrophilic substitution reaction, it gives 2 products. One is ortho product as well as para product. Why you are going to get ortho product and para product during electrophilic substitution reactions of phenol? Observe the resonance structures of phenol. During resonance, the carbon atom at ortho and para position acquire negative charge. Observe here, during resonance, phenol is stabilized by resonance. How many resonance structures are possible for phenol? The 5 resonance structures are possible for phenol. And in that, you observe structure 2nd, structure 3rd as well as structure 4th. There is a negative charges are present at which position? Ortho, para, ortho. Because of that reason, electrophiles attack ortho position as well as para position as to ortho position, and phenol is more reactive than benzene towards electrophilic substitution reaction. Therefore, phenol is more pronounced towards electrophilic substitution reaction than benzene because of the presence of OH group. Therefore, phenol undergo electrophilic substitution reaction to give a mixture of two products. One is ortho products, another one is para product. Now, let us consider nitration. As we know that nitration means the organic compound is heated with nitric acid in the presence of concentrated sulfuric acid. Here in case of phenol, I am going to consider two cases under nitration. The first one with dilute nitric acid. Second one with concentrated nitric acid. When you heat phenol with dilute nitric acid at low temperature of 298 Kelvin, So, nitration, under nitration of phenol, we have to discuss how many cases? Two cases, case 1 and case 2. In case 1, when phenol is heated with dilute nitric acid at 298 Kelvin, you will get a mixture of ortho and para product. We will get a mixture of orthonitrophenol and para-nitrophenol. Ortho will get 15% as well as 30 to 40% you will get para-nitrophenol. Now, when you consider this as a phenol, it is heated with nitric acid, dilute nitric acid at 298 Kelvin. So, one in phenol, so in ortho position nitro group goes, as well as secondary it goes to which position? Para position, as well as there is a formation of water, Therefore, when phenol is heated with dilute nitric acid, at 298 Kelvin, you will get a mixture of orthonitrophenol and para-nitrophenol. Already you know that under haloalkanes and haloarine chapter, I discussed that when ortho and para isomers are formed, which is the major product? The major product is para. Here observe how much of para-nitrophenol is formed. 30 to 40% of para-nitrophenol is formed, 15% of orthonitrophenol is formed. This is the case 1. How does phenol reacts with dilute nitric acid? Once again, I will repeat, my dear student, when phenol is heated with dilute nitric acid at 298 Kelvin, you will get a mixture of orthonitrophenol and para-nitrophenol. Why the position ortho and para only gets substituted by electrophile? Already you observed while writing the resonance structures of phenol, the carbon atom present at ortho and para position acquire negative charge. Case 2. Now, this ortho and para isomers which are formed together, how can you separate? It can be separated by steam distillation. Already you know that the separation methods in the first PUC under the chapter basic principles and techniques in organic chemistry. Already you know about distillation. Under distillation, there are 4 types of distillation: simple distillation, fractional distillation, steam distillation, and vacuum reduced pressure distillation. Ortho and para isomers are separated by steam distillation. Why? Ortho isomer as well as para isomer is separated by steam distillation because orthonitrophenol is steam volatile due to intramolecular hydrogen bonding. Para-nitrophenol is less volatile due to intermolecular hydrogen bonding. My dear student, in the previous session, in the 6th session, I discussed that in hydrogen bonding, we have 2 types of hydrogen bonding: intramolecular hydrogen bonding and intermolecular hydrogen bonding. Intramolecular hydrogen bonding is present in orthonitrophenol. In para-nitrophenol, intermolecular hydrogen bonding is formed. When intramolecular hydrogen bonding is formed, it is steam volatile, more steam volatile. When intermolecular is formed, it is less volatile. So, because of the difference in the hydrogen bonding intra and inter, they can easily separated by using one beautiful technique. The technique is known as what? Steam distillation. Therefore, orthonitrophenol and para-nitrophenol, they can be separated by steam distillation. This is, observe the structure here. It is a intra, inside the molecule. It is inter, between 2 molecules, This is the one molecule of nitrophenol. This is another molecule of nitrophenol. Between 2 molecules, there is a formation of hydrogen bonding. It's an intermolecular hydrogen bonding. It is intramolecular hydrogen bonding, that is inside the molecule. But here, this is between two molecules. Okay? Once again, I'll repeat, my dear student. Ortho and para isomers are separated by steam distillation. Orthonitrophenol is steam volatile due to intramolecular hydrogen bonding. Para-nitrophenol is less volatile due to intermolecular hydrogen bonding. Next, with say case 2 with concentrated nitric acid. What happens when phenol is heated with concentrated nitric acid in the presence of concentrated sulfuric acid? You will get in the same ring ortho, para, ortho positions are substituted by nitro, NO2 plus. Here electrophile is NO2 plus. Therefore, this NO2 attacks which position? Ortho, para as well as ortho. This is second position, this is fourth position, and this is sixth position. It will form 2, 4, 6 trinitrophenol. 2, 4, 6 trinitrophenol. It's a yellow crystalline solid and it is commercially called as picric acid. Commercially called as picric acid. Although it is called as acid without COH group. Name an acid which does not contain COH, but it behaves as an acid, and the beautiful example is picric acid. Observe the structure of picric acid. It does not have COH group, although it is called as acid because of the 3 groups. Nitro groups are electron withdrawing groups. Already I discussed that when electron withdrawing groups are there, the acidity increases. Electron donating groups are there, acidity decreases. Because of the 3 nitro groups, they are more acidic. Therefore, it has acidic nature. Therefore, it is the commercial name of 2, 4, 6 trinitrophenol is picric acid. Is known as what? Picric acid. So, what's the IUPAC name of picric acid? IUPAC name of picric acid is 2, 4, 6 trinitrophenol. Trinitrophenol. How can you convert phenol into picric acid? The very important board question. How do you convert phenol into picric acid? Phenol is converted into picric acid by heating with concentrated nitric acid in the presence of concentrated sulfuric acid. Next, halogenation. In halogenation, we have to consider bromination. First, let us consider aqueous medium. First case, let us consider aqueous medium. Second case, in the presence of non-polar solvents like carbon tetrachloride or carbon disulfide. Under bromination, I am going to consider 2 cases. First case, in the presence of aqueous medium. What happens in the presence of aqueous medium when phenol is treated with bromine water? It will give rise to 2, 4, 6 tribromophenol. It is a white precipitate. What's the color of 2, 4, 6 trinitrophenol? It is a yellow color precipitate. 2, 4, 6 ditribromophenols. It's a which color precipitate? White color precipitate. Here the substitution takes place in the same ring at ortho, para and ortho position. What's the very important thing? It is in aqueous medium, that is in the presence of water. Bromination, halogenation takes place to form white precipitate of 2, 4, 6 tribromophenol. But same reaction, if I repeat in the presence of non-polar solvents such as carbon tetrachloride and carbon disulfide. The substitution takes place in different ring. One in ortho position, another one is in para position. We'll get a mixture of orthobromophenol and parabromophenols. Parabromophenols is major, orthobromophenols is minor. They can be separated by steam distillation. Therefore, under nitration, we have to deal with 2 cases. That is first with dilute nitric acid and second one with concentrated nitric acid. With bromination, that is with bromine water, we have to consider 2 cases. First one in the presence of in aqueous medium. Second one in the presence of non-polar solvents like carbon tetrachloride or carbon disulfide. Next, the very important reaction is, naming reaction is coal-base reaction. In coal-base reaction, first you convert phenol into sodium phenate. So, phenol is converted into sodium phenate. Next, this sodium phenate heated with carbon dioxide at 413 Kelvin. Under a pressure of 6 to 7 atmospheric pressure 6 to 7, we will get sodium salicylate. Which on acidification, it gives rise to salicylic acid. What's the IUPAC name of salicylic acid? 2-hydroxybenzoic acid. Therefore, what is coal-based reaction? In coal-based reaction, first you convert phenol into sodium phenate. Phenol into sodium phenate. How do you convert phenol into sodium phenate? Phenol can be converted into sodium phenate by heating with sodium hydroxide. Then this sodium phenate is heated with carbon dioxide at 413 Kelvin under a pressure of 6 to 7 atmosphere. You will get sodium salicylate, which on acidification give rise to salicylic acid. Next reaction is Reimer-Tiemann reaction. Here also convert first phenol into sodium phenate and heat with chloroform. Heat with chloroform at 340 Kelvin. Here also we have to convert phenol into sodium phenate by heating with sodium hydroxide. Then you have to add chloroform. Formula of chloroform is CHCl3. At 340 Kelvin, phenol becomes sodium phenate, ONA, and this one hydrogen takes one chlorine and there is elimination of HCl and it will become CHCl2. This further reacts with 2 moles of sodium hydroxide. The nucleophile chlorine is replaced by OH. Nucleophile chlorine is Cl2 become OH twice. When any compound which containing more than one OH group, they are unstable. From that, we have to eliminate water. From that, if I eliminate water, CHOH twice becomes CHO. Aldehyde groups. This is sodium salicylaldehyde. Sodium salicylar, which on acidification give rise to salicylaldehyde. Salicylaldehyde. Therefore, in coal-based reaction, we converted phenol into salicylic acid. In Reimer-Tiemann reaction, we converted phenol into salicylaldehyde by using chloroform and sodium hydroxide. Instead of chloroform, if you use carbon tetrachloride and sodium hydroxide, we won't get salicylaldehyde, we are going to get salicylic acid. Therefore, phenol is converted into salicylic acid either by coal-based reaction or by Reimer-Tiemann reaction. When you use chloroform, you will get salicylaldehyde. In the place of chloroform, if you use carbon tetrachloride, you are going to get salicylic acid. You are going to get salicylic acid. Next term. How do you convert phenol into benzene? See, this is the structure of phenol. When phenol is heated with zinc test, it takes oxygen and it will become ZNO, and phenol is converted into benzene. Like, how do you convert phenol into benzene? By heating with zinc dust. So, the very important question, name a product form when phenol is heated with zinc dust. When phenol is heated with zinc dust, it is converted into benzene. The last reaction, oxidation of phenol. When you consider phenol, it gets oxidized in the presence of chromic acid. How can you get chromic acid? By the mixture of potassium dichromate and concentrated H2SO4. Potassium dichromate and concentrated H2SO4 give rise to chromic acid. It will give rise to benzoquinone. They are alpha beta unsaturated ketones. What are benzoquinone? Alpha beta unsaturated ketones. Similarly, phenol can be converted into benzoquinone by oxidizing in the presence of air. Like, what are the two methods to convert phenol into benzoquinone? Phenol can be converted into benzoquinone by the oxidation in the presence of chromic acid or oxidation in the presence of air. Okay. Therefore, what are the uses of phenol? Phenol is a powerful antiseptic in soaps and lotion, manufacture of Bakelite, manufacture of Dettol, and pharmaceutical products such as salicylic acid and aspirin, as well as manufacture of dyes like phenolphthalein and picric acid. These are the uses of phenol. Phenol is used in the manufacture of antiseptic soaps and lotions, as well as the manufacture of one of the important polymer called Bakelite, in the manufacture of Dettol, and parasitical products such as salicylic acid and aspirin, as well as phenolphthalein and picric acid. Therefore, my dear student, in this session, I completely deal with phenols. In the next session, I'll come up with third family, that is ethers. Therefore, next session, that is in the 8th session of this chapter, I'm going to deal with the third family of this chapter, that is ether. Until that, goodbye. Thank you. Have a nice day.